The entangled state is one thing. It's not two particles. I think in a deep sense, entanglement isn't spooky. It challenges to rethink what we mean by locality.
Hello, everybody, and welcome back to Chasing Consciousness. So today, we're going to be trying to get our heads around one of the most extraordinary phenomena ever recorded in subatomic physics, quantum entanglement. Famously dismissed by Einstein as spooky action at a distance, it has since been proved to exist over and over again in the lab. This non-local phenomenon is when particles remain connected so that their physical properties continue to affect each other, no matter what the distance is between them. It's been in the news a lot recently, not only because it's been photographed by a team at the University of Glasgow, but also because a host of successful so-called teleportation experiments in which entanglement has been used to send information instantaneously between two computer chips that have absolutely no causal connection between them whatsoever. I believe that the implications of this phenomenon are basically among the most important scientific discoveries of our time. Most importantly, to update our purely classical cause and effect understanding of the world. But it does beg an important question. Through what medium is that information passing between those two entangled particles, if not through space and across time? So to help us get our heads around this mind-bending reality today is theoretical physicist Dr. Chris Fields. Dr. Fields is an independent scientist interested in both the physics and the cognitive neuroscience underlying human perception of matter in space and time, very simply. He began his career as an experimental physicist, obtaining his PhD in the philosophy of science at the University of Colorado. And he was an early developer of the automated DNA sequence analysis tools at the Human Genome Project. He's published over 130 peer-reviewed papers in nuclear physics, artificial intelligence, molecular biology, and cognitive psychology. So I have been pondering this question of entanglement ever since I first heard about it. So I literally couldn't wait to get into this with Dr. Fields. So without further ado, let's go. So, Dr. Chris Fields, welcome to Chasing Consciousness, and thank you so much for joining us. How are you?
Well, thank you. I'm very well.
And you're in France, I understand, not in the States.
Right. In a tiny village in the south of France where I can see the Pyrenees from my upper window here.
Oh, stunning. Well, listen, Chris, thank you so much for coming on to help us with this really quite extraordinary topic that I think the general public are dying to understand better about entanglement, the entanglement of distant particles and how they seem to be connected in a way that we don't quite understand. But before we get into that, give us a quick overview of your career. What are your research areas? And maybe what's your big passion? What got you into physics in the first place?
Well, probably like a lot of kids, I got into physics from amateur astronomy and telescope making and a fascination with the night sky, combined with just a general curiosity about how things work, which I think also drives a lot of people who get into sciences in general.
Absolutely.
And my career has been a real random walk across various disciplines. I spent a good deal of time in the Human Genome Project, for example, working on software systems for analyzing DNA.
Wow.
And actually came back to physics only about 10 years ago.
Mm-hmm. And what are your research fields in physics?
I take a very informational approach to physics. And so I'm interested in physics as a theory of information transfer between systems.
Mm-hmm.
So physics as a way of talking about communication between entities.
Yes.
I work in quantum information theory, decoherence. I'm starting to do some work in quantum gravity.
Wow. That's the big one, isn't it? So, Chris, if you were to try and choose the thing you're most proud of in terms of getting a bit of feedback, getting a bit of interest from the rest of the field, what are you most proud of in terms of conclusions that have rocked the boat, maybe?
Actually, I think the most significant thing I've done professionally was to emphasize very strongly and very early on in the Genome project that data analysis had to be fully automated.
Right. And why is
And
that significant?
that, well, it means, for example, that today in our current pandemic situation, for example, people are able to analyze DNA from hundreds of sequences in real time.
Right.
And understand what's going on a daily basis, as opposed to having to wait months to years to figure out what's happening because analytical techniques are so slow. Now, certainly, I can't take credit for that. My contributions were much longer ago when the problems were not nearly so significant. It was a sea change in the way people thought about analyzing biological data that happened in the early 90s.
Yeah. Well, Chris, if you don't mind, let's get straight into the meat of today's conversation. So, entanglement has been in the news a lot recently. First, with this instantaneous teleportation of information between two separate chips in a lab in Bristol, in UK, and then later last year with China's extraordinary achievement of teleporting information between a ground station and a satellite over 100 kilometers high up into the atmosphere. And listeners, we're hoping we're going to speak to the Chinese head scientist of that, who's my age, which is just bonkers, really, how young these incredible scientists are who are working with this totally ridiculous new technology. Starting with the broadest possible definition, shall we say the sort of textbook definition, Chris, what is entanglement? How was it discovered? And how has physics' understanding of it evolved over the last 100 years? Because if I understand correctly, it was quite a controversial one at the beginning when Einstein was about.
Well, the idea of entanglement first appeared in Schrodinger's work.
Yeah.
And so I think that Schrodinger was actually the first to understand it. And the idea is actually very simple. A system is in an entangled state if you can know everything there is to know about the system,
Mm-hmm.
and yet have no knowledge of its parts.
Right.
So entanglement is the exact opposite of what's called separability.
Yep.
And a system is separable if you can know about its parts.
I see.
And in fact, know everything there is to know about its parts. So entangled systems are systems that are not separable. Entangled systems are systems for which you don't have access to information about the parts.
So was this originally observed, or was it theorized about and then later discovered to be true?
Well, it was not observed in a way that anyone knew that they were observing it or understood in what way they were observing it.
Mm-hmm.
Entanglement is characteristic of quantum systems, but it takes a very delicate experiment to see it explicitly.
Yes.
And that experiment was, in a sense, designed by Einstein, Podolsky, and Rosen in their paper claiming that quantum theory, because it allowed entanglement, was incomplete. And their philosophical position was, if you can't learn about the parts of a system, your theory must not be a good theory.
Yeah.
Or it must not be a complete theory.
Mm-hmm.
But the approach that they took eventually led to the aspect experiment, which was the first experiment that actually demonstrated entanglement in the laboratory. And that was the prototype for all the experiments that we've seen since then that have been over longer distances, that have closed various loopholes, ruled out various alternative explanations to entanglement as the explanation. And these experiments are really the most sensitive, direct tests of quantum theory that we have.
So can you just maybe give us a little example of what is actually happening when they alter the state of one particle and they see a difference in another, just so we can sort of get a visual on it? I mean, quite impossible at a quantum level, but certainly something we can imagine.
Well, the way these experiments work, essentially, is one has a source that produces an entangled state.
Mm-hmm.
And informally, we can think about an entangled state as a pair of particles that are correlated in a certain way.
Yeah.
Now, that way of thinking about it is useful, but it's actually wrong. And I think it causes a lot of confusion.
Mm-hmm.
But one has this source that produces an entangled state, and one produces an entangled state that expands very quickly.
Mm-hmm.
So typically you're producing, for example, entangled photons. So they're moving away from each other at the speed of light, or you're producing entangled electrons and they're moving away from each other very quickly, very close to the speed of light. And then you have detectors that are set up far enough apart that they can't communicate by a light signal.
Yeah.
In the time that it takes the particles to reach the respective detectors. So that closes a particular loophole. It means that there's no classical communication going on between the detectors. And what one sees when one does that kind of experiment is a level of correlation between the results obtained at the two detectors that is larger than one would expect on classical grounds.
Yeah.
And the correlation is not just between the states of the particles, between the parts of the entangled state, even though I just defined an entangled state of one for which you can know nothing about the parts. So that's this whole way of talking about parts of an entangled state is not really accurate. But it's also the response of the entangled state to what the experimenters do in the two locations.
Mm.
So a key aspect of this experiment is that the experimenters at the two locations have to be able to independently change the question they're asking about the entangled state. And it's the super correlation that one doesn't expect classically is that the detector, the two experimenters are always called Alice and Bob, right? The super correlation is that what Bob sees depends on how Alice has chosen to measure her side of the entangled state, even though Alice and Bob cannot communicate.
So we have what might be, if we follow this, what you're saying is a mistaken thinking, we have a bit of an observer problem.
Yes. But the extent to which it's a problem, I think, really does depend on this importation of the idea of parts.
So, Chris, just before we get into that, talking about non-locality and how maybe the way we're interpreting this phenomena is at the heart of that problem, tell us a little bit about this famous maxim that Einstein said, this is spooky action at a distance. What made Einstein call it that? And why was he so derisive about this? Why did he just throw it out?
Oh, well, I think if one looks back at Einstein's career, and this is a historical observation that I think, if I recall correctly, Nicholas Geisen made. Einstein's career was about removing from physics the idea of action at a distance. And so he was driven by this idea of locality. And if one goes back to Newtonian physics, Newtonian physics incorporates action at a distance in the form of gravity. And gravity in Newtonian physics is just a force. It has a name and it has an equation, but it doesn't have a physical explanation. It just exists. And it acts out to infinite distances. So it gets weaker and weaker as you get farther and farther away. But it doesn't have a time component. It's meant to be acting instantaneously.
Yeah.
So the sun exerts a gravitational force on the Earth in classical physics, and it doesn't take any time for that force to get to the Earth. And now, if you think about Einstein and the special theory of relativity, basically what the special theory of relativity says is that it takes time for information to propagate through space. And information only moves at the speed of light. The photon is the most efficient carrier of information.
Mm-hmm.
So that must apply to gravity too. So this is one driver of the theory of general relativity, is to try to turn gravity into something that's local as opposed to something that's acting at a distance.
Yeah.
So if you replace the idea of gravity with the idea of space-time itself being curved, having a particular shape, then the gravitational action of the sun on the Earth, what the sun does is curve space-time in the vicinity of the Earth. So the Earth now just detects that curvature locally. So now the action of gravity is not this force reaching out over a long distance instantaneously from the sun to the Earth, but it's rather something that the Earth measures locally by just responding to the curvature of space itself. So Einstein was the person who got rid of action at a distance in his theory of gravity, and the understanding that photons were the transmitters of the electromagnetic force got rid of action at a distance in electricity and magnetism. So action at a distance was temporarily gone from physics. And then quantum theory seemed to reintroduce it.
And do you think that these observations justified everybody saying that actually Einstein had been wrong? Or are we going to get into that in a minute when we start talking about how this has been misinterpreted?
Well, I think that quantum theory systematically challenges all classical intuitions.
Yeah.
Up to and including the intuition that space itself is a fundamental feature of the universe.
Mm.
And
yeah, which we're about to get into, actually. Chris, this brings us beautifully on to the next question because it really regards this. So from the point of view of us as a general public who don't necessarily understand how this works, it really looks like a non-local phenomenon because, there literally isn't time for this information to pass between these two particles. It looks like there is some conduit of this information that isn't classical, that just doesn't follow the linear space-time thinking that we're used to in a local context. So that's the way it looks to us. But is it possible that we've just really misunderstood what local means? Because it seems from the theory of general relativity and the way quantum theory then comes back against that, it seems that this sort of the fact that space and time really aren't as linear as we're led to believe by our senses, does that completely undermine what non-local actually means? Maybe we've just got this idea of what is local and non-local wrong. And if so, can you tell us, is entanglement actually a non-local phenomenon? Is it spooky?
I think in a deep sense, entanglement isn't spooky. In a deep sense, it challenges to rethink what we mean by locality,
right,
and to go even more deeply than relativity theory did into the idea that space itself is local in some sense. So let's go back to the idea of entanglement being about two particles and see really what's wrong with that idea.
Mm.
I mean, the idea is that I'll have to use my hands here. Right?
Thank you. We've got no board for you to demonstrate. I'm afraid.
And two little things come apart from the source, and there's nothing in between. That's what our particle intuition tells us. That after the photons leave the source, there's nothing in between. They're two little individual identifiable things out here.
Right.
Now, that's precisely the intuition of separability. That's precisely what's not correct in thinking about entanglement. So that's why I tried to say the source creates an entangled state and the state itself expands. So that if you think about Alice and Bob with their two detectors, Alice is effectively operating on a rigid object. So she's taking something like an I-beam and twisting it. So it's no surprise that the other end of the I-beam over on Bob's side moves, because it's one thing, not two things.
And in that sense, are we looking at a similarity between the matter of these particles, if we can even consider them as matter, and the space through which they're moving? It's almost as if the space is part of the same continuum.
Yeah, I mean I think that's a good way to put it. So let's think about this not from our perspective, but rather from the perspective of the entangled state.
Yeah.
Right? The entangled state is one thing. It's not two particles. And so the source produces the entangled state. From its point of view, it's just sitting there. It's not doing anything at all. It's just a state. It's been produced. And then all of a sudden, from out of nowhere, these two laboratories collapse onto it. So the state doesn't, from its point of view, there's no motion. There isn't any space because there isn't anything for there to be space between, right? They're not two particles. There's nothing in there. There's no empty space. So we, in our laboratories, have tools for measuring space. We have meter sticks, we have clocks, we have those sorts of things which help us distinguish one place from another place and one time from another time. But this entangled state doesn't have any of those tools. It doesn't see any passage of time. It doesn't see any distance. It has no way to measure distance. So it just exists. And then all of a sudden it doesn't when these two laboratories collide on top of it and annihilate.
It's so difficult to imagine, isn't it? It's really, really hard for us because our senses are so attached to the linearity of time and space. Let's
Right.
move on, Chris, to this idea of spin. Now, if I've understood correctly, spin is all about is the way that we define submolecular particles. What exactly is spin? And can we kind of use an idea of spin? Is it analogous to an idea of frequency? And does that suggest that there's some sort of resonant phenomena going on between the various spins of various particles across the universe? Is there a resonance phenomena in this concept of spin? What is spin?
From a technical point of view, spin is just a variable that has two possible values that you can call up and down.
Right.
And classically, spin is associated with rotation,
Yeah.
with angular momentum, with an actual object like the Earth.
Right.
Spinning around. And that creates a vector that resists being moved. So if you're riding a bicycle or something, the wheels are spinning, that helps you keep your balance on the bicycle.
Right.
And that classical concept was imported into quantum theory.
Mm-hmm.
Because quantum theory needed this extra variable to characterize a particle. And the variable always takes one of two states. So the variable behaves mathematically like an angular momentum that can either be pointing up or pointing down, or pointing north or pointing south. So the mathematics of a rotating body was just imported into the theory.
So in fact, it's actually quite a mistaken image in terms of helping people to understand what's actually going on at the quantum level.
It's somewhat useful, but somewhat misleading,
Right.
as so many things are in trying to go from classical concepts to quantum concepts. But there are now many, many things that are called spin in quantum theory. So to pick one example, there's something called isospin. And a state that's isospin up is a proton, like the nucleus of a hydrogen atom. And the state that's isospin down is a neutron. So
well,
you can
I ask because I understand that it's used in the measurement of entanglement experiments. Is that correct?
Yes. Yeah. Spin is by far and away the easiest kind of a thing to measure in that kind of experiment because it's manipulable by the apparatus. And the results are always up or down in some direction. And when we talked earlier about Alice and Bob being able to choose how they measured what was going on, what they're choosing in the standard experiment is what direction to define as up.
And do you think that when we see a change in one particle, theoretically beyond any kind of classical information exchange, is it possible that there's some sort of resonant phenomena going on between those two particles, or am I on the wrong tack by thinking in that way?
Well, again, there aren't actually two different particles. It's actually
Yes.
just one object.
Absolutely. We've just got to try to change our imagination here, haven't we? It's so difficult in a classical world. Okay, well, that brings us nicely on to information, because obviously what is happening here is an exchange of information at some level. And I know this is a concept you've worked with a lot. You spoke a little bit at the beginning about some of your computer science work. How has the concept of information influenced modern physics? And do you think it's a useful tool in terms of trying to help us to really understand what's going on at a quantum level and understand what's going on, at the level of the true fabric of reality?
I think it's a very useful concept. And indeed, the last couple of decades have seen a number of attempts to reformulate physics completely in information theoretic terms. And I think this, in a sense, is the wave of the future for physics. And many people, physicists and also philosophers, are exploring the idea that information itself, not particles, not space-time, not material in any sense, but rather information itself is what is, in a sense, fundamentally real.
Yeah.
And my own position on the relationship between quantum theory and information is that quantum theory is not a theory of objects at all, but quantum theory is a theory that tells us what is required for observers to extract information from some system that's being observed.
Yes.
So that quantum theory itself is about the movement of information and the resources necessary to move information from one place to another. And by resources, I mean things like energy and time.
And that, it seems to me that information is a really good way of drawing a parallel between what's being exchanged at this physical level you've just mentioned about, interaction, energy, matter, cause and effect, this sort of thing. But it draws a parallel between also the exchange between what's happening there and observers and consciousness itself. Now, in physics, that's been a big problem, hasn't it? The observer effect, and it's caused all of this debate over, the double slit experiment, and everybody getting very riled up about the problem of consciousness and the problem of observation. But it seems to me that information has this wonderful sort of unifying ability to bring together these two types of information, if you like, as a single idea. Can you map out for us how you've used this idea of information to arrive at your conclusion that consciousness must be fundamental to the physical world?
Well, I think what thinking about physics or thinking about other sciences in terms of information does is to disallow this backing out of the situation that characterized classical physics and characterizes classical sciences in general. I mean, you mentioned the observer effect. The observer effect is very common in psychology and biology and these other fields. So it's not unique to physics.
No.
And in, say, psychology, it's just understood that how you ask questions affects what sort of answer you get. And what the informational outlook in physics does is enforce the same way of thinking, that what kind of question you ask influences what kind of answer you're going to get from the world. And
Sure.
John Wheeler was probably the first to make this completely explicit. He was fond of saying things like, if you don't ask a question, you're not going to get an answer. So if you don't actually do an experiment, if you don't actually do something to the world, you're not going to get anything back. So that's a way of emphasizing that the observer is interacting with what is observed, and there's information flowing from the observer into what is being observed. And that the experimenter is acting on the world in some way by asking a question.
Mm-hmm.
And the world is then giving an answer back. So it's a very small step from there to think of the world as observing the observer, to think of the world as just another participant in this conversation, and to see observer and world as just exchanging information.
Mm-hmm.
If I'm doing an experiment, I'm giving information to the world effectively by acting on it. And the world is giving information to me by acting on me. So there's no information flow without interaction. And that information flow is bidirectional.
So you're saying that an interaction in terms of energy and matter really fundamentally has no difference than an interaction in terms of mind and consciousness.
Right.
Can you give us an example that sort of, because that sounds very abstract, can you give us an example that would show how fundamentally it's the same kind of information? Because it seems different, doesn't it? I mean, like if you tell me I've got this hat in the background and I think it's a kind of beige color, that I can't really understand that in terms of anything except the qualia, that is a perception. It is a conscious interpretation. That's not the same thing as a cause and effect interaction, is it?
Well, we have these two different languages and I'm not sure how different they are.
Yeah.
If you talk to an experimental physicist, for example, I used to work at an accelerator laboratory. And so how do you talk about what's going on as, say, a beam of protons travels through some complicated plumbing arrangement that moves it this way and that, as if it was a stream of water? It's almost impossible not to talk about the proton moving along and feeling a magnetic field and responding to it by moving in some direction. And then, sensing an electric field or feeling an electric field and moving in another direction. So it's a metaphor that we fall into very naturally when we try to take the point of view of some other entity.
Mm.
And so I think what this language is challenging us to do is to take other points of view and try to imagine the sensory world of possibly very simple things like electrons that are sensitive to electric and magnetic fields, and that's about it.
Mm. I mean, presumably that could work the other way as well. You know, there's a lot of neuroscientists out there arguing that consciousness is an illusion, that this is just an exchange of neural firing and chemicals in the brain. Presumably, we could argue it the other way and say that actually consciousness is just an energy and matter interaction as well, and that therefore consciousness sort of really doesn't exist. It's just a physical process. Couldn't that also work the other way, Chris?
Well, yeah, you could also say that it's all consciousness and that energy and matter don't exist. I mean, the question is whether there's anything productive in talking that way.
Yeah.
I don't think there is. There's always the temptation to find the one master language that expresses everything to the exclusion of all other languages. And I think that's probably not a sensible thing to be looking for.
So you think that in a way, information is a kind of neutral language that sort of avoids the necessity of having to take the plunge either way and saying consciousness is fundamental or physicality is fundamental. We can just talk about information and say, listen, we just don't know what's fundamental. Let's just work with information because that allows us to press forward.
Yes and no. Information is a very useful language. But when we talk about information, we very naturally tend to hide the distinction between semantics and syntax.
Hmm.
And classical information theory, as developed by Shannon and others in the mid-20th century, is all about the amount of information that you can move from here to there. And if you talk about the conservation of information in physics, then one's talking about conserving the amount of information. So, for example, one might claim that if Alice and Bob are communicating, then they're exchanging equal amounts of information. So the communication channel is symmetrical.
Mm.
Now, that's just about the amount of information. But what we're really interested in is what the message means to the sender and what it means to the recipient. And those may be completely different. And in human conversation, often they are.
And that definitely brings us towards more of a consciousness take on things, doesn't it? Because, you know, information in a kind of physical system should be fairly predictable.
Well, again, we may want to dissociate predictability from meaning.
Right?
I can predict to some extent how a conversation partner is going to respond to the meaning of what I say, the meaning for me.
Yeah.
So I can predict a little bit about the meaning for the hearer, for the conversation, for you. But that doesn't mean that our conversation is meaningless.
Right.
So predictability and meaning are not opposing concepts. So if we suppose we think about our proton traveling down a beamline in an accelerator, what's the meaning of the magnetic field? It may be turn left. And we can predict that. But that doesn't mean that our ability to predict it doesn't mean that it doesn't mean turn left to the proton, sorry.
And what about the observer effect, where we find that as soon as we introduce an observer, they're not doing anything, they're just perceiving, we get different results and we seem to have affected the system? Presumably, that's a pretty good argument for consciousness having a very active role in these interactions.
Well, again, the the key idea here is that observation is interaction. There's
Right.
no such thing as a passive observer, and this was Wheeler's point, was saying no question, no answer. The only way to get answers, to actually get information from the world, is to ask questions, to interact with the world. So in classical physics, we have this idea of observers almost as gods, who are able to act completely precisely with no side effects whatsoever on the world, to do exactly what they want and not do anything unexpected or unintended,
Mm-hmm.
and then to stand back and watch the results unfold completely with no other influence. But that's not what observation is actually like. The observer is embedded in the situation, and the phenomenon being observed may be much smaller scale or much larger scale than the observer. So I may be looking at some other galaxy, for example, some very big thing, in which case I'm looking at light that's very old. But nonetheless, I, as an observer, exist in the world. I'm interacting with the world that I'm receiving information from. I think there's a great reluctance to state things in a way that suggests that experiments are not reproducible, or possibly not even possible. But I also think that all physicists understand at some deep level that Wheeler was right, that this idea of the observer being completely abstracted from the situation isn't really viable.
Yeah.
And I have lots of discussions with colleagues, some of whom are physicists, some of whom are psychologists, some of whom are biologists, about the meaning of objectivity and the extent to which this ideal of objectivity is achievable, and what intersubjective agreement means, and that sort of thing.
Mm.
And these are topics that I think increasingly are being discussed in public.
Well, panpsychism is most definitely becoming far more popular, not only among physicists and among philosophers, which I think is perhaps slightly more predictable, but we're starting to see biologists who are usually behind the curve on this more philosophical thinking and much more physicalist about these things. We're starting to see them come in and start to support this kind of thinking, because it can seem quite abstract and quite theoretical. But the way you put it, that really, the answer to these non-local phenomena, the answer to the observer effect, and the answer to all of these conundrums we see in the double slit experiment, is really to just understand that actually they're the same kind of interaction. It seems so simple, and it leads so clearly and so kind of obviously to a panpsychist position. Why do you think it's received? Why do you think that the mainstream take, which is basically the Copenhagen interpretation, why is it such a stretch for them, this kind of thinking? What is it that just stops them from taking that step? I mean, is it so ambitious? maybe it is quite strange to be as open-minded as some of us are. Maybe one of those scientists would come back at us and just say, you're out of your mind. You're thinking too abstractly. We need to work on observables. But it seems like it is observable. What is it that's stopping people moving in this direction, despite the fact that it is becoming more popular?
I think probably mostly tradition and training. From a physics point of view, there's this phrase, "shut up and calculate," that's sometimes attributed. I think was originated by David Merman, and the idea of that was, don't ask these philosophical questions. Just figure out how the theory works. Be practical. And I think that attitude was actually a disaster. I think it put back understanding aspects of the theory that have only come to the fore in the last couple of decades. Because people did ask these more fundamental interpretive questions.
Well, it does seem rather strange to have a mathematical model to reflect reality if, when you come to ask, okay, so what does that tell us about reality, you actually can't say anything. It does seem essentially useless. But it seemed to me that the Shut Up and Calculate school was just so interested in kind of what we might call institutional science, just in terms of sort of getting the funding and can, make sure the equations add up and, keep teaching. And it seemed that there was almost a kind of conformism, a kind of herd think, a group think problem going on. When do you see there being a change there? What do you think was the turning point? You mentioned the last 10 or 20 years. What started to happen in the last 20 years that started to see that table turn? What kind of theories were trailblazing that slight change that we're seeing?
Well, I guess I would personally at least, put a lot of the credit here to John Archibald Wheeler and his work.
I agree.
And, his lineage went very deep to both Bohr and Einstein.
Tell us more about his ideas that managed to bridge a gap between the Copenhagen crowd and the rest of us.
Well, he was the first to popularize the idea of what he called the participatory universe, which was the idea that physical systems are question askers and answer receivers, and they're all in there asking questions and receiving answers, so interacting by information exchange. And that's what physics is about. And that was Wheeler's idea.
Well, I interviewed particle physicist John Butterworth, who's definitely on the sort of Copenhagen side of this. And when I put to him some quotes from Schrödinger, basically saying there is no doubt this, consciousness must be fundamental, he was skeptical. But then when I mentioned Wheeler's idea of the participatory universe, he said, I can handle that, And he also admitted that there were deeply uncomfortable questions with the wave-particle duality. So I think that you're absolutely right. Wheeler was right there, wasn't he? Somehow bridging this potentially unbridgeable gap between the consciousness as fundamental supporters and the more traditionalist Copenhagen supporters, with this wonderful kind of half and half solution of the participatory universe. However, I'd like to get your opinion. It sounds to me like the participatory universe is kind of panpsychism in disguise. do you agree that he was more or less arguing a panpsychist point of view, that consciousness was fundamental, or do you think he was trying to not go quite that far?
Well, maybe this is interpreting him a bit liberally, but I don't think it's in disguise at all. I mean, it seems perfectly straightforwardly panpsychist to me. And looking back, beyond Wheeler, what's called the Copenhagen interpretation is I think attributed to Bohr fairly sloppily. I mean, it's the interpretation that grew out of the textbooks.
Yeah.
Bohr's thinking was very subtle and very influenced by Kant, especially. I think even by William James.
Yeah.
And so I think Bohr's thinking and Heisenberg's thinking also, and certainly Schrodinger's thinking.
Well, of course.
At what is life, and he's quoting the Upanishads and so on. Those people were certainly not crank turners.
Well, I am extremely interested to come back to this in part 2. Chris, thank you so much for allowing me to sort of rip you from side to side here, because there's so many things playing into the implications of entanglement. So please, listeners, do stick around, because we're going to be going right into Chris's work also on meditation, because Chris is a long-term meditator and has a book out about that. We're going to be going deep into the implications of entanglement as Chris is interpreting it. And we're going to be talking about duality and non-duality. We're going to be talking about knowledge. So stick around, guys, to find out really what does this all mean. And these are the questions which the shut up and calculate guys never want to ask, because their calculations just don't answer those questions. So let's go there. And thanks again, Chris. We'll be back in a minute.
Okay, excellent. Thank you.
So welcome back to part 2 with Dr. Chris Fields of today's interview about entanglement. We've had an amazing part 1, everybody. So do please, if you're new to this subject, go back to part 1 and listen to Chris's eloquent description of how entanglement entered into the literature, how it may have been slightly misunderstood, and how there could be potentially a better way of thinking about that, and how information, particularly information, which, by the way, guys, we're going to be doing a whole episode on information theory, really helps us to unify these sometimes completely dissociated ideas of observer and physical interaction. But now for this part 2, we really want to get into the implications. We want to get into the meat. A lot of the time, the scientific world is, shall we say, a little cautious to draw interpretations from their results. Again, Chris, in part 1, mentioned tradition. Quite often, scientists are just literally afraid from parting from tradition in case they will sort of become pariah and potentially even excluded from funding and from potential positions in universities. So me and Chris, we're not scared of this, are we? So we're gonna go straight in and start looking at these questions and say, listen, what does this actually tell us about the nature of reality and the nature of what it is to be a conscious being? So Chris, thank you. Welcome back. Thank you once again for part 1. Very, very eloquent. But let's get into the really real bag of worms here. We spoke about entanglement. It's very unclassical, or maybe it's the real classical and classical's got it wrong. What exactly are the implications of entanglement the way you see it? And what questions do we need to answer to kind of unpack that?
Well, I think this idea challenges us to think very deeply about what the process of exchanging information with another system is. What does it really mean to interact with the world? And what does it mean to receive information and receive it in a way that is distinctive? So when any of us hear words in a conversation, we may not know what the word means, but at least we typically know what word we heard. We don't just hear sound. So what does it mean to receive information? What does it mean to give information, to transmit information to the world? And what is this world that we're interacting with? So recall that I by saying that an entangled state is a state that we can know everything about without knowing anything about its parts. And I think a first thing to do is to ask ourselves what we really know about the system that we call the world, that each of us calls my world, that we're interacting with. So if I think in my own case, I'm at all times interacting with my world, which I can characterize as everything in the universe except me, leaving it open what the word me means. But I know that there's something else, and that's what I'm interacting with. And I receive information from my world, this something else, and that information is classical. It consists of discrete, identifiable experiences that I can remember.
So they're linear in space and time.
That, well, let's
sorry.
Let's leave that aside. I can keep track of experiences as they arrive. So I have my own time counter. How that relates to time on clocks is another matter.
Yeah.
Since clocks are outside of me, they're just in this world. So the fundamental question is, besides the fact that we receive this input, what do we know about the world? And this is a question, of course, that philosophers have been asking for millennia. And the answer to this question that almost every philosophical tradition seems to arrive at in one way or the other is that we actually know nothing about the world except the information that we get from it. And you can turn that around and say, and that means the world knows nothing about us except the information that it gets from us.
Yeah.
So the world and I are on exactly the same footing here in terms of knowledge. We're two systems, we're exchanging information, and we each know about the other only the information that's been exchanged. So how does this relate to entanglement? If we think of our interaction with the world in this way, that we know about the world only what the world has given us, then in particular, we know nothing about the world's parts. We're not interacting with any of the world's parts. We're interacting with the world as a whole.
Mm.
And the information we receive from the world, we then organize into a bunch of discrete categories, which we call physical objects or other people or other organisms or whatever. We cut the world up into these chunks, each of which is given a boundary. So we treat the world as separable.
So maybe a newborn baby, for example, wouldn't see it in that discrete way. It would be a kind of blurred mass.
Well, there's the famous phrase of the blooming, buzzing confusion. I'm not quite sure who that was, who quite originated that phrase. And is the world of an infant a blooming, buzzing confusion? Current evidence suggests that it's much less of one than was thought by, even as long ago as the 50s, by, say, Piaget. Infants at birth seem to already recognize many of what we would regard as the ordinary characteristics of the world. I think a useful question is the question that I think Wittgenstein originally asked about the motion of the sun. The pre-classical physics idea, of course, is the world is flat and the sun moves around the earth and you see it come up and you see it set. The alternative theory is that the earth moves around the sun. And Wittgenstein's question was, so what would it look like if the earth were moving around the sun as opposed to the sun moving around the earth? And the obvious implication is it looks exactly as it does, right? If all you do is see sunrises and sunsets, you can't distinguish the two at all. So the reason for bringing this up is that what's the difference between a theory in which the world has structure independently of us and a theory in which we impose structure upon an unstructured world? And if all we can do is make observations, then those two are indistinguishable. We can't tell just from making observations where the structure comes from. This is an aspect of a very general phenomenon. And interestingly, the science that brings that phenomenon closest to home is computer science. In a sense, the entire idea of computer science is multiple realizability. And it was people like Turing and Church who founded computer science who first realized this, that any computation can be executed on any of a huge variety of kinds of hardware. So if what you're interested in is the behavior of something, that behavior can always be implemented in an arbitrarily huge number of different ways. And by just looking at the behavior, you can't tell how it's being implemented. And in the case of our interaction with the world, we can't open up the world and see how it works on the inside, because opening up the world is just making more observations. It's just moving this interface in some way or manipulating the interface in some way. It's not getting rid of the interface altogether.
So, Chris, do we have a problem then of coming to any conclusions about the nature of reality?
I think that's exactly what it means.
However, a question, Chris, if you are suggesting that we have a fundamental unity between the interaction between an observer and something in the physical world, or between two elements of the physical world, or between two observers. They're essentially all interactions. They're all the same thing. They are inseparable in that sense. As we noticed when we spoke about these two particles that are entangled, they are essentially inseparable. And we make an error when we see these two particles moving separately as being entangled in some sort of non-local way. They are, in fact, really the same thing. If that is, in fact, the case, isn't the information that we are receiving and observing and transmitting, isn't there also a non-separation between those two things as well? So in some sense, the information is already transmitted. I already have the information. Isn't that one of the implications of your take on entanglement?
Well, I think a way to put that is that whether things are entangled or separable is a matter of perspective and point of view.
Right.
So if I'm observing you interacting with your world, and I'm observing, of course, from within your world, but I can split my world into you and everything else, then I can say, as a theorist describing this situation, the combination of Freddie and Freddie's world is in an entangled state, and there's no information moving between them. They're just one entity with no separation. Or I can say, okay, I'm going to choose to regard Freddie as a separate entity. And in this case, I can describe his interaction with his world as communication. I can take either of those stances.
So in that sense, what we have is a kind of dual track way of seeing the world, where it's useful for us to talk about separateness and an exchange of information and interaction. We can think about that, and there could be an exchange. But equally, if we look at the fundamentals, we find that actually that information is already present. And in a way, that interaction is wholly unnecessary because the information is already available. The reason I mention this, Chris, is because something we're going to be looking into on the podcast is remote viewing. The technique developed by Ingo Swann and some physicists at SRI in the 1970s. Have you heard of remote viewing?
I've heard it. I know nothing about it.
Well, the phenomena is very, very simple. It's a form of psychic phenomena where people are able to see in their mind's eye information distant not only in space, but also sometimes in time as well. So they are given an anomalous target, a code usually, and the operator knows what that code refers to, and they then tune in with that target. What I find absolutely fascinating about this phenomenon is not only the results that they were getting, which have been statistically analyzed and obviously very effective for the American military because the program ran from the 1970s until the mid 90s. It ran for a very long time and was well funded by all of the lettered agencies. The reality of this kind of phenomena, should it prove to be true, as I hope to investigate on the podcast, is that in a sense, whilst we are in an interactive world where there is a separateness, that separateness must in some way be an illusion in some way, because it seems that these certain people who have stronger results than the average person, interestingly, they found out that everybody can do this to a certain extent. It's just that some people are particularly talented. That essentially they have access to this information in some way, even though there would be no way in a separateness model, in an interaction model of them having access to it. And I wonder if there isn't some possibility of a kind of two-tiered world, a kind of two-tracked world in which we have some form of physically interactive and separate world, but that it's actually operating on a kind of entangled, unseparate base. and that this information becomes disentangled and becomes separate through our embodiment. What do you think? Do you think there's a possibility that we have a kind of two-tiered reality here?
Well, I think the question of how the world works is, of course, the question that drives all of science. But I think it's almost undeniable that we have these two perspectives on how the world works. And one is, as you put it, the perspective of separate entities. And we have to take perspective if we want to think of ourselves as entities that, in some sense, are well-defined, that have particular identities, and that have pasts and futures and sets of experiences, and so on. But on the other hand, we have this conception of the world as a completely coherent, connected, single entity that just is doing whatever it is it's doing.
Mm.
And that we're at best kind of fuzzily definable components of that world, that we're completely interpenetrant with that world, that energy and matter are constantly flowing through us in exchange with that world, that our boundaries really aren't well defined at all, and that the boundaries of anything else aren't well defined at all.
That sounds pretty two-tiered to me. Would you agree?
Yeah, I think it's very useful here to in fact go back into classical physics, into the thinking of Laplace, who was somewhat after Newton, but who I think first very clearly understood the philosophical consequences of Newton's laws. Newton's laws describe these mechanistic interactions between entities. And Newton's laws involved action at a distance, as we described earlier. And Laplace, I think, immediately understood that if the universe is in a sense, a contraption of entities that interact according to these fixed laws, and that forces act at infinite distance, then information about the state of the whole system is encoded in every part, because every part is in the state it's in only because the whole thing is in whatever state it is in as an entire whole. And making any change anywhere, because all of the forces have infinite range, affects everything.
Right.
So there is no sense of an isolated system other than as an in-practice approximation that's sort of good enough for government work.
And that was actually confirmed by Pauli's energy principle, wasn't it? That if you make a change of the level of energy, it changes all of the other particles in the universe. So that's actually been confirmed by quantum physics many years later, hasn't it?
Well, confirmed in a mathematical sense.
Yeah, well, yeah. Chris, if you don't mind.
It's built into this sort of idea that information is never lost is built into quantum theory.
Chris, if you don't mind, I'd like to speak a little bit about integration of these kind of ideas. I think one of the most challenging things about quantum physics for the general public is that it undermines so many of our quotidian experiences. It goes so heavily against our classical viewing of the world on a day-to-day basis. And I don't think that entanglement is any different by your definition and by the implications that we've just been discussing. What I wanted to mention was that it's very interesting to me seeing entanglement before it's even entered the kind of group consciousness, if you like, the general public's thinking and understanding of the world. We have it being used in technology. So now, of course, we've got quantum computers, and we've also, more specifically to entanglement, we've got these photons being used to transmit information on using entanglement, which of course will lead to very highly encrypted information transfer, very, very useful in today's world of information hacking. So there's lots of applications of entanglement here. And I thinking back into history, it seems that it's quite often that a concept that was really quite, people were a bit skeptical about, particularly I think the religious conservatives always sort of skeptical about these new phenomena discovered in science. Take electricity, for example, or radio waves. There was this demonic understanding of electricity at first, that it was some sort of evil demonic energy being harnessed by these evil scientists. But as it entered into technology and everyday life, it became just an everyday thing. Do you think that the extraordinary implications of entanglement and quantum theory in general will have the same sort of path, that as these start to get used in quantum computers and in quantum communications, we'll just see this becoming part of everyday understanding, and the classical view will start to open up into a slightly more sort of dualistic quantum/classical thinking?
That's a very good question. And I think the number of places in technology where one, in a sense, has to have some quantum intuitions is still fairly small.
Yeah.
But it may be growing as the recognition of phenomena that need quantum thinking to understand in, say, biology becomes more clear. And there are now well-documented aspects of things like human decision-making that really make sense only in terms of quantum theory. And it's also the case that as quantum theory is reformulated in different ways, we may find that it's more familiar to us. And so its implications may be hidden in plain sight, shall we say, in things like context dependence and the observer effect as it's seen in
which we've covered on the show.
In all areas of life.
Absolutely.
So what it may do is just loosen the grip of an idea of objectivity, which was never accurate in the first place, and that exists essentially as a mythology of again the observer as a kind of God that is able to act completely precisely and then observe without influence, without influencing anything.
So you think that the advance of these kind of technologies starting to normalize, shall we say, some of the implications of quantum theory and entanglement, do you think that in a way physicalism as a pure philosophy, as a very reductive philosophy, as followed by the kind of scientistic, the scientism kind of approach, do you think its days are numbered? Do you think that the public will just slowly start to open up to these less physicalist views that we seem to have been indoctrinated so heavily into as school children?
Um, well, I suspect that eventually the um, the ideas of classical materialism will start to go away.
Hmm.
I always worry about using the word physicalism because it's so ambiguous.
Yeah, yeah.
But the idea of classical materialism, that the world consists of a bunch of more or less independent hunks of stuff that behave in sort of interesting ways, is so far, I mean, that's 100 years out of date already, even in physics. And that's not an idea that's all that useful. Where I think that the ideas of quantum theory may be more helpfully absorbed into the general thinking in society is in viewing the world in a sense more biologically, as in viewing all actions as having not just unknown but unknowable side effects.
Mm-hmm.
And in recognizing that systems in general are highly nonlinear and are unlikely to behave in ways that simple models would have us expect them to behave.
Mm.
You know, I think these are the sorts of lessons that this kind of physics will actually end up injecting into the culture in general.
Well, I think it's long overdue, and given how long quantum theory has been about, it really is taking a little while. So I hope that this podcast and wonderful work like the work of Chris's will help with that. Chris, I am appalled at myself that it's taken me this long to get to your book. But the book is not about quantum physics, so I suppose I can be forgiven slightly. Um, and it is very much about, again, mind, isn't it? So tell us about the book you've co-authored with your wife about meditation. What's it called? And we're going to be interviewing quite a few neuroscientists about meditation, the positive effects, the effects inside the brain, the benefits for cognition, and the benefits for against mental health issues, and even immunity. Tell us a little bit. What's your book about, and what are you hoping to communicate with it? And tell us what it's called and where we can get it.
Well, I should first say that the book really is Allison's idea, my wife, Allison Tinsley. And the idea came out of going to one of the many science and non-duality meetings that we've been to and talking to people about their meditation practice. And the book's called Meditation. If you're doing it right, which is a slogan, a very lovely slogan that a friend of ours once used about working together in the kitchen. And it's a book of interviews, not unlike this one, with people about what their meditation practice is like.
Oh.
And the people that we interview range from some fairly well-known figures like Deepak Chopra to people you've never heard of, who are just friends of ours from somewhere, who've been meditating for a long time.
Mm.
And it's really an exploration of the variety of practices that people use and the variety of experiences that people have in using them. And it's held together by the phenomenon that meditation is useful for well-being.
At almost every level, I imagine.
Yes. And it has different kinds of outcomes in different people. But of course, that's what you would expect.
And
because
how long,
there are different people.
How long have you meditated, Chris?
Goodness. Probably about 12 years. And so I'm not really a long-term meditator as that goes. I mean, some people have been at it for 30 or 40 years.
And how did it change the way you saw the world? Did you find that some of the mental states, the states of mind, literally, that you came to, not necessarily during your practice, but also as a consequence of your practice, did you see a shift in the way you perceived the world and in the kind of physics you were considering as possible?
I would say that it's one of its fundamental effects, at least for me, but for a lot of people, is an increased openness to what the world is trying to tell us. A good meditation is like a long walk in the woods, except you do it in half an hour in your living room. It's a way of in a sense, stopping thinking and starting listening. Yes. I think that's the important thing about it.
And do you think that there's a suggestion towards, through meditation, do you think there's a suggestion towards some of these slightly non-dual, these slightly more non-separate states that we've been discussing as implied by entanglement? Do you think that meditation gives us some hints in that direction? I mean, obviously there's a lot of tradition, Eastern tradition, that kind of talks about non-separation. Do you think that meditation as a phenomena of mind takes us towards that kind of understanding of the world?
Yes, and I think the neuroscience evidence here is very good. That, in fact, one thing that meditation is helping us do is to understand how we create that sense of separation.
Yeah.
Understand it at the level of neuroscience, at least. So it's clear that meditation is one technique among many. And I would include not just psychedelics, but what are called flow activities, anything that's a very engaging, externally directed kind of activity.
Yep.
They break down the boundary between the self and the world by defocusing attention on the self. They tend to turn off or turn way down the parts of the brain that construct this representation of the self and the interests in the sense of self-interested, the interests of the self in meeting its own particular goals or in achieving its particular status or whatever.
Do you think it
So
really? Do you think it really
meditation
matters?
systematically turns that kind of stuff off.
Absolutely.
And so what it allows is a focus on the world as a whole without the self being regarded as this little piece of it.
Do you think it really matters fundamentally which is true? I mean, obviously, in philosophy and in science, we're always desperately trying to work out what is actually there, what is actually true, what is actually real. But does it actually really matter if, to what extent we are actually constructing and how illusory these separations may be? I mean, the bottom line is the reality of embodiment is that those separations are in place. So, does it really matter which one of these two possible realities is fundamental? I mean, surely we can just work with both. And meditation is rather a wonderful way of hopping between the two and maybe harvesting the benefits of both.
Um, I certainly agree with that. And when I think of things being fundamental, I tend to think of it from a kind of epistemological perspective
Yeah.
as opposed to an ontological perspective. And I think it's the epistemological perspective that's more useful because that's the one we can do something about.
Yeah, that's the knowing rather than the being, isn't it? Yeah.
Right. We can do something about what we know and how we think about what we know.
Well, that brings me on to knowledge. I mean, it's such a conundrum, isn't it, when we think about this sort of what we might call a kind of relativity of what we know, how difficult it is to jump from what we know, from the epistemological to the ontological, from what we know to what actually is. The question I wanted to ask was about mystical experience, sometimes called peak experiences, religious experiences, deep moments of, psychedelic experiences where these separations literally do break down and the self kind of dissolves. These experiences can give us a lot of knowledge about this non-separate world. However, scientific experimentation and the scientific method doesn't work with that. So which side do you fall on? I mean, Jung, somebody we'll be covering quite a lot on the show, particularly in this first series where we'll be talking about the communal unconscious, we'll be talking about synchronicity. Jung was very, very clear as a clinical psychiatrist that he felt that there was a limit to which the scientific method couldn't go beyond, and that beyond that area, the mystical and the symbolic was something that science couldn't penetrate. It couldn't really make conclusions about. Do you think that that's the right approach? This, let's face it, we fall into a dualistic position there, and the separation between the physical world and the soul, or however you want to call that duality. Do you think that's the best way of looking at it, or do you think it's better to say, actually, the structure, the reality that mystics have reported for millennia through their mystical experiences actually just has a structure, a science that we have yet to discover? Is it better to think of it in that unified kind of way, and therefore leaving hope open to a unified theory? Or do you think it's better to do as Jung did and said, listen, this is mysterious and it's designed to be mysterious. It should always remain mysterious and you should never pretend that you can know anything about that. What's the best approach?
Well, I think that science always gets into trouble when it pretends to be about ontology. So I suppose the first thing I would say is ontology in science is purely pragmatic. And The second is something about how science works. All ideas in science come from somewhere. And that somewhere is often, I believe, what people like Jung, for example, are talking about when they talk about intuition or the collective unconscious or enlightenment experiences or however you want to describe these kinds of experiences of just suddenly getting an idea out of nowhere. At least from your conscious experience, it's out of nowhere. That's where ideas come from. And the scientific method is a methodology for testing ideas. It's not a methodology for generating ideas. The scientific method, in a sense, recognizes that great ideas occur to you when you're taking a bath or out walking in the woods or meditating or something. So now, okay, you've got this great idea. What do you do with it? You try to figure out whether it's correct in some sense, or useful, or gives rise to a model that helps you do something. Build buildings or cure diseases or whatever it is that you want to do. So the scientific method is about experimental test. It's not about where the idea comes from in the first place. So this raises the question of, can we then have a science that addresses where ideas come from in the first place? And if so, what would it mean to test ideas about where ideas come from in the first place? And in a sense, that science exists. It's called positive psychology, for example, or the neuroscience of meditation, or aspects of cognitive science. And we know a lot about the situations that typically give rise to good ideas in humans. And we know that they typically involve relaxation, positive affect, low stress, and so forth. Curiosity. Do we know how those conditions give rise to good ideas? Not yet. Will we learn more about it? Probably. Will this sort of investigation give us the final answer on where good ideas come from? My guess would be no. There may be no final answer. I don't know.
So we could be being naive to hold out for a unified theory where we do actually have the ability to understand the full picture going right into the realm of spirit, mystical experience, non-separateness. We could be being naive, and therefore potentially, from your point of view, Jung's approach might be a better approach? It's untouchable. It's mystic. It's not to be talked of in terms of cognition.
See, I always think it's a bad idea to rule phenomena out of court as not to be investigated.
I quite agree.
But I also agree that it is naive to imagine that any system with finite resources can figure out how it itself works.
Right.
completely. So that leaves us in a situation that one could regard as deplorable, but one could also regard as really interesting and fun, in that we're blessed with this motivation of curiosity. And as long as we don't know what's going on and we're curious, it gives us something to do.
Yes, yes. What a beautiful, beautiful way of looking at it, Chris, that curiosity can only be there if we haven't got all the answers. And as stimulating and fascinating as all of these phenomena coming from, shall we say, the world beyond the scientific method, can just keep us asking questions and keep us curious, and just keep those anomalies coming, so that we have to continue trying to integrate greater and greater models that include more and more of this stuff. What a beautiful way of thinking of it, fun and exciting. Thank you, Chris. Chris, thank you so much for your time and for your enthusiasm for all of this, because it is so difficult to ask these more difficult questions and to come up with reasonable answers that do bring into focus all of the various elements and all of the various arguments without getting all wrapped up and tangled and into a right old stick. So I hope, listeners, that this has been interesting and has helped you map your own ideas about this and sort of come a little bit closer to the implications of entanglement and quantum theory to our daily lives, and to the way that we start to interact with what we might call the unknowable, what Jung called beyond the realm of science. So please, listeners, go out, get Chris's and his wife's book, Meditation. If you're doing it right. Have I got that right, Chris? Is that the title?
Yes, absolutely.
I'm going to say it again because it's such a good title. Meditation. If you're doing it right. It's just a brilliant tagline. So go out and get that, guys. Some really interesting and quite diverse takes, by the sound of it, on meditation. And you can always catch Chris, if I understand correctly, at the Science and Non-Duality Conference. He gives some fascinating presentations there. And it just leaves me to say thank you, Chris, again. And I hope we get the chance to catch up if there are more developments on this in the second series and on into the podcast. So thank you for your support, Chris.
Well, thank you very much. This was a lot of fun.
Well, brilliant.
And good luck going forward.
Thank you very much. I really appreciate it, Chris.